April 2024. A paper gets published in a journal called Classical and Quantum Gravity. Peer-reviewed. Real physics. 6 authors. The lead author is a physicist named Jared Fuchs, a graduate of the University of Alabama in Huntsville, working in collaboration with a New York-based research group called Applied Physics. The paper is titled Constant Velocity Physical Warp Drive Solution, and what it says in the dry, careful language of theoretical physics is essentially this. A warp drive is mathematically possible within the known laws of physics. No exotic matter, no negative energy, no violations of Einstein's equations, just geometry, just mass, just the curvature of space-time. Now, before you close this video thinking this is another breathless piece of science journalism, hang on, because the story isn't what most headlines made it out to be. This warp drive doesn't go faster than light. It can't, at least not yet, and probably not for reasons you'd expect. The actual story is stranger, more frustrating, and somehow more fascinating than the headlines. It starts not with a solution, but with a prison. The scale of the problem. Let's start with a number. 25 trillion miles. That's how far it is to Proxima Centauri, the closest star to our sun. Not the closest interesting star. Not the closest star with a potentially habitable planet. Though Proxima does have those. Just the closest star. Period. 25 trillion miles. For context, the distance from New York to Los Angeles is about 2,800 miles. The distance from Earth to the Moon is about 239,000 miles. The distance from Earth to the Sun, which already feels incomprehensibly large, is about 93 million miles. Proxima Centauri is 25 trillion miles away. Light itself, the fastest thing in the universe, moving at 186,000 miles per second, takes over 4 years to get there, 4 years at the speed of light. That's not a trip. That's most of a U.S. presidential term, spent doing nothing but traveling at the absolute maximum speed the laws of physics allow. And you'd arrive at the closest star to ours, Voyager and the tyranny of distance. In 1977, NASA launched Voyager 1. It is the most distant human-made object in existence. Right now, as you're watching this, it's traveling through interstellar space, beyond the heliosphere, beyond the bubble of our sun's influence, at about 38,000 miles per hour. 38,000 miles per hour. That's roughly 15 to 20 times the speed of a rifle bullet, depending on the weapon. At that speed, Voyager 1 would reach Proxima Centauri in approximately 73,000 years. Think about that for a moment, not as a statistic, as a human reality. 73,000 years ago, Homo sapiens were making cave paintings in what is now Europe. Agriculture didn't exist. Writing didn't exist. Every civilization in human history, every empire, every religion, every war, every invention, all of it fits inside the window of time it would take our fastest spacecraft to reach the nearest star. And Voyager isn't slow by any earthly standard. It's just that space doesn't care about earthly standards. The rocket equation. So why can't we just go faster? Build a bigger rocket. More fuel. More thrust. The answer is something called the Tsiolkovsky rocket equation, named after a Russian schoolteacher who derived it in 1903. And it is, in the most literal sense, a tyranny. Here's the problem. A rocket accelerates by throwing mass out of its back end. Newton's third law. The heavier your fuel, the more thrust you get. But here's the catch. You have to carry that fuel with you, which means you have to burn fuel to move fuel, which means the more fuel you add, the more fuel you need to move that fuel, and then more fuel to move that fuel, and it spirals exponentially. If you wanted to accelerate a crewed spacecraft to even a modest fraction of the speed of light using conventional chemical propellants, the kind that launch Apollo, the fuel requirements become, in technical terms, absurd. The rocket would need to be almost entirely fuel, not mostly fuel, not 90% fuel. We're talking mass ratios that would require more hydrocarbons than exist on Earth and every gas giant in the solar system combined. Chemical rockets are extraordinary machines for getting off a planet, for crossing interstellar distances. They're about as useful as trying to cross the Atlantic Ocean by swimming. The alternatives and their walls. The 20th century produced some genuinely creative thinking about this problem. Project Orion developed in the late 1950s and early 1960s, proposed something almost magnificently insane: a spacecraft propelled by nuclear explosions detonating behind it. Not metaphorically, literally exploding atomic bombs, one after another, against a large pusher plate. Physicists calculated it could theoretically reach around 3% of the speed of light, which would get you Proxima in about 140 years. Uncomfortable, but not impossible for a generational mission. The project was canceled largely for political reasons, specifically the 1963 Partial Nuclear Test Ban Treaty, and because, as it turns out, governments are reluctant to detonate thousands of nuclear warheads in low Earth orbit. Fusion propulsion is more elegant. Instead of bombs, you burn hydrogen isotopes in a controlled reaction, the same process that powers stars. The theoretical efficiency is vastly better than chemical rockets. The problem is that we haven't yet built a fusion reactor that produces more energy than the total energy consumed to run it. Recent milestones of the National Ignition Facility, where the laser energy delivered to the fuel target was exceeded by the fusion yield, are genuine scientific progress. But the facility still consumes far more energy overall than it produces, and we remain a long way from a practical power source. We've been working on this for about 70 years. We're getting closer, but closer is not there. Antimatter is even more efficient. When matter meets antimatter, they annihilate completely, converting 100% of their mass into energy, exactly as Einstein's equation E equals mc squared describes. In principle, antimatter propulsion would be the ultimate rocket. In practice, we can produce antimatter in particle accelerators. We produce it in nanogram quantities at enormous expense, and it must be stored in magnetic containment fields because it annihilates on contact with literally anything. At current production rates, accumulating enough antimatter for an interstellar mission would take longer than the current age of the universe. That is not a figure of speech. And then there's Breakthrough Starshot, a real, funded initiative launched in 2016 by Russian billionaire Yuri Milner, with Stephen Hawking and Mark Zuckerberg serving on its board of directors. The concept: fire an extraordinarily powerful laser array at a tiny spacecraft, essentially a chip on a sail, and accelerate it to 20% of the speed of light. The math works. The engineering is brutal, but not obviously impossible. At 20% of light speed, you've reached Proxima in about 20 years. There's one significant catch. The spacecraft weighs a few grams. You are not on it. Scaling Breakthrough Starshot to carry a crewed vessel would require a laser array that consumes more power than the entire current electrical output of human civilization, and a light sail hundreds of miles across. The physics scales. The engineering does not. The wall. So here is where humanity stands. We can reach other planets. We've landed on the moon. We put rovers on Mars. We've sent probes past every planet in the solar system, past Pluto, past the edge of the sun's influence. We've done extraordinary things. And the nearest star, the nearest one, is so far away that every approach we've tried either fails on paper or works only for objects the size of a postage stamp. For decades, the standard response from physicists was, "This is just how the universe is." The speed of light is the cosmic speed limit. Interstellar travel for human beings is probably impossible on any timescale that matters. We are, in a very real sense, prisoners of our solar system. Then, in 1994, a young Mexican physicist finishing his PhD at Cardiff University asked a different question. Not, how do we go faster? But, what if we didn't have to? Einstein's actual rule: to understand what Miguel Alcubierre did, you have to understand what Einstein's speed limit actually says, because most popular explanations get it slightly wrong. The special theory of relativity, published in 1905, doesn't say nothing can move faster than light in some universal, absolute sense. What it says is more specific. No object with mass can accelerate through space to reach the speed of light, because doing so would require infinite energy through space. That's the key phrase. The rule applies to objects moving through space. It says nothing, or at least far less, about space itself moving. And here's the thing: space does move. We've known this since Edwin Hubble's observations in the 1920s confirmed that the universe is expanding. Distant galaxies aren't flying through space away from us. Space itself is stretching, carrying those galaxies with it. Galaxies far enough away are receding from us faster than light. Not because they're moving through space at that speed, but because the space between us and them is expanding faster than light can cross it. This is called metric expansion, and it's not a violation of relativity. It's a different phenomenon entirely. Alcubierre read this and thought, wait, if space can expand, can it also be compressed? And if so, what happens if you compress in the right way, in the right place, around a spacecraft? The bubble, what Alcubierre published in 1994 in the journal Classical and Quantum Gravity, was a specific solution to Einstein's field equations. The equations that describe how matter and energy warp the geometry of space-time. His solution described a bubble, a region of flat space-time. Think of it as a small pocket of normal, undistorted space, surrounded by a region where space-time is warped in a very specific way. Ahead of the bubble, space is compressed, contracted. Behind the bubble, space is expanded, stretched. The result is that the bubble and anything inside it moves forward, not because anything inside the bubble is accelerating. The bubble itself is being carried along by the geometry of space-time around it, like a surfer carried by a wave. The surfer isn't powering through the water. The water is moving, and the surfer moves with it. Inside the bubble, the laws of physics are completely normal. There's no acceleration, no g-forces, no time dilation of the kind you get from approaching the speed of light. The astronauts inside wouldn't feel a thing. They'd just be sitting there, and the universe outside would be rearranging itself around them. And critically, from the perspective of an outside observer, the bubble can move at any speed, including faster than light, because the bubble isn't violating the rule against objects moving through space faster than light. The bubble is moving space itself. The mathematics was correct. Alcubierre checked it. Other physicists checked it. The solution genuinely satisfied Einstein's equations. For about 30 seconds, this was the most exciting thing in theoretical physics. The catch. Then people looked more closely at what the solution actually required. To create the warp bubble, to compress space ahead and expand it behind. The mathematics demanded a region of space-time with negative energy density, not low energy. Negative energy. Energy less than zero. In general relativity, there are what are called energy conditions, essentially mathematical constraints describing what normal matter and energy look like. Real stuff has positive energy density. These are called the weak energy condition, the null energy condition, and a few others. Alcubierre's bubble required violating all of them simultaneously. And when physicists ran the numbers on how much of this negative energy material you'd need, they got an answer so large it was almost meaningless. To power an Alcubierre warp bubble around a spacecraft the size of a car, you need negative energy roughly equivalent to the total mass energy of the observable universe. Not the Earth, not the Sun, not the galaxy. The entire observable universe. Everything we can see in any direction, converted into some kind of hypothetical negative energy substance. This is not an engineering challenge. This is physics telling you, in the clearest possible terms, no, by most accounts, that should have been the end of the idea. A beautiful mathematical curiosity that happens to be physically impossible. It wasn't. Van den Broek's geometry trick. In 1999, a Belgian physicist named Chris van den Broek looked at the energy problem and noticed something. The amount of negative energy required wasn't a fixed physical constant. It was a function of the bubble's geometry. Specifically, it was driven by the size of the bubble's outer surface relative to the volume of space inside it. And in general relativity, you're allowed to do something that sounds completely impossible. You can have a large interior with a tiny exterior. This isn't science fiction. It's a consequence of curved space-time. The classic analogy is a sphere whose surface is much smaller than the volume encloses, which is impossible in flat Euclidean geometry, but perfectly fine in curved space-time. Van den Broek proposed a modification to Alcubierre's metric. Keep the interior of the bubble large enough to fit a spacecraft, but make the exterior, the boundary of the bubble, visible to the outside universe, microscopically small, about the size of a proton. When he ran the numbers, the required negative energy dropped by 20 orders of magnitude. That's not 20%. That's a factor of 100 quintillion. From the mass energy of the observable universe down to roughly the mass of Jupiter. Still impossible by any near-term engineering standard. But suddenly, the idea had moved from mathematically absurd to merely extremely difficult, which in physics is meaningful progress. Harold White and NASA Eagle Works. For the next decade, warp drive research remained mostly in the domain of theoretical papers. Interesting, occasionally cited, not exactly a priority for space agencies. Then in 2011, a NASA engineer named Harold White, working at a small advanced propulsion laboratory at Johnson Space Center called Eagle Works, published an analysis of the energy problem. White took Van den Broek's geometric insight and pushed it further. The key observation was about the bubble's wall, the region of warped space-time between a flat interior and normal exterior. In Alcubierre's original formulation, this wall was thin. White found that if he made the wall thicker and distributed the energy density more smoothly across it, the total energy requirement dropped further. He also changed the shape. Instead of a sphere, White's optimized bubble was toroidal in cross-section. The exotic matter was distributed in a ring-shaped shell surrounding the spacecraft, rather than concentrated in a thin spherical layer. The result, by White's calculations, the required exotic energy dropped to roughly 700 kilograms, a figure most other physicists considered optimistic at best, comparable in mass to a large motorcycle but contested in method. This was either a remarkable breakthrough or a sign that something was off in the analysis. Physicists were divided. White's optimization relied on assumptions about how you could configure the energy distribution that some researchers considered questionable. The Eagle Works team also attempted a laboratory experiment, using a device called an interferometer to try to detect microscopic space-time curvature around a set of high-voltage capacitor rings. The results were ambiguous, and later analysis suggested the signal they observed was more consistent with thermal noise than actual space-time distortion. But whatever you think of the experimental work, something important had happened. Warp drives had entered the conversation of mainstream theoretical physics, not as science fiction, as a legitimate, if extremely challenging, area of inquiry. Applied physics and the classification problem. Around 2021, a research group called Applied Physics, based in New York, decided to approach the problem differently. Instead of starting with a specific metric and trying to optimize it, they asked a more fundamental question. What is the complete space of physically possible warp geometries? What are the mathematical constraints that any warp solution must satisfy? And what's inside those constraints? The key paper from this period was by Alexei Bobrick and Johnny Martiri, published in Classical and Quantum Gravity. They introduced a systematic classification of warp drive spacetimes, dividing them into superluminal and subliminal categories, and identifying which energy conditions each type required. The subliminal category, warp drives that travel slower than light, turned out to be more tractable. Some configurations in this category came close to, but still violated, the standard energy conditions. They were getting closer to something. They just hadn't found it yet. The 2024 solution. In April 2024, Jared Fuchs, working with Bobrick, Martiri, and 3 colleagues, published a paper that opened this video. Constant velocity physical warp drive solution. What they found was a specific geometric configuration that satisfies all the classical energy conditions of general relativity. No negative energy, no exotic matter, no violations of known physics. Just a stable shell of ordinary positive energy matter, the kind of matter the universe is made of, combined with particular distribution of what they called a shift vector. The way Fuchs described the underlying principle is worth understanding. Contrary to the popular description of warp drives as contracting space ahead and expanding it behind, what's actually happening in this solution is different. The energy in the shell is moving, rapidly circulating around a passenger volume. And this movement creates a gravitational effect, a kind of conveyor belt, that carries whatever is inside the shell along with it. Fuchs compared it to a smoke ring. The ring itself moves through the air not by pushing against anything, but because of the circulation of the fluid composing it. The team used an open-source numerical tool they developed called Warp Factory to analyze the energy conditions across the entire space-time geometry. The output confirmed it. No regions of negative energy density. The solution was, in the technical language of the paper, physical. For the first time in 30 years of warp drive research, someone had found configuration that didn't acquire anything that doesn't exist. The critical asterisk. And here's where intellectual honesty requires a pause. This solution is subliminal. It travels slower than light, not slightly slower. The physics of the configuration doesn't allow it to break the light barrier without reintroducing the negative energy problem. As Fuchs was careful to clarify, this warp drive avoids exotic matter precisely because it operates within certain geometric constraints, and those constraints are incompatible with faster-than-light travel. What they found is real. It's not a rounding error. It's not a loophole that secretly violates something. It genuinely satisfies the energy conditions. But the ship it describes cannot exceed the speed of light. So why does this matter? Two reasons. The first is conceptual. This is the first time anyone has shown that warp-like space-time geometry can exist without exotic matter. That's a genuine result. It doesn't solve the faster-than-light problem, but it proves that the family of solutions is larger than previously thought. Future researchers have new territory to explore. The second reason is practical, and it's more interesting than it might first appear. A subliminal warp drive, one that travels at, say, 90% of the speed of light, or 50%, or even 10%, would be a fundamentally different kind of spacecraft than anything we've imagined. The crew inside the bubble would experience no acceleration. They'd exist in flat, normal space-time, while the geometry outside rearranges itself. No g-forces during acceleration, no physical stress on the ship from maneuvering, and at relativistic speeds, something interesting happens to time. A trip to Proxima Centauri at 90% of light speed would take about 4.7 years from Earth perspective. But for the crew inside the warp bubble, because of relativistic time dilation, less time would pass. Perhaps 2 years, perhaps less, depending on the exact configuration. You'd leave Earth and arrive at another star, and less time would have passed for you than for the people you left behind, closer to home. At even modest fractions of light speed, the solar system stops being impossibly large. Mars trips in days, Jupiter in weeks. Outer planets that currently take years to reach become accessible on timescales that make crude exploration genuinely practical. The Fuchs solution doesn't give us the stars. Not yet, but it suggests a path, a framework within known physics. That makes the question feel less like a fantasy and more like a very hard engineering problem. There's a significant difference between those two things. Let's say someone solves it. Let's say 20 years from now, or 100 or 500, a physicist finds a configuration, the geometry that allows a warp bubble to break the light barrier while satisfying all the energy conditions. The full solution. The one Alcubierre was reaching for. You build it. You climb inside. You engage the drive. Here's what happens. Problem 1. The ship you can't steer. The moment your bubble crosses the speed of light, something changes in the geometry around it. A boundary forms at the front wall of the bubble, a surface beyond which cause and effect become disconnected from the interior. In general relativity, this is called a causal horizon. You're familiar with the concept from black holes. The event horizon, the boundary beyond which nothing can escape, what forms at the leading edge of a superluminal warp bubble, is structurally similar. Information cannot cross it from outside going in, which means light cannot cross it, which means signals cannot cross it. This is a problem because of where you are sitting. You're inside the bubble. The engine, whatever generates the warp geometry, is part of the bubble's wall. The front of the bubble, the part compressing space, is ahead of you, and the causal horizon sits at that front wall. To change course, you need to modify the geometry of the bubble. To modify the geometry, you need to send a signal to the systems generating it. But any signal you send from inside the bubble toward the front wall cannot cross the horizon. It arrives, hits a boundary, and stops. You cannot turn the ship. You cannot slow down. You cannot stop. This was first analyzed rigorously by physicists including Sergei Krasnikov in the late 1990s and examined further by researchers including Ken Olam and others in subsequent years. The general conclusion in the literature is that a superluminal warp bubble, once activated, cannot be controlled from the inside. The crew becomes passengers on a projectile with no brakes and no steering wheel. To stop the bubble, you need to modify the geometry from outside. from the destination or from a relay point that could somehow interact with the bubble's exterior. How you coordinate that, given that the bubble is traveling faster than any signal you could send ahead of it, is a problem that does not currently have a solution. This alone would make superluminal warp travel effectively unusable, but it's the least dangerous of the three problems. Problem 2. The radiation that would vaporize the crew. In 1974, Stephen Hawking published a calculation showing that black holes aren't entirely black. The event horizon, the causal boundary of a black hole, interacts with quantum field in the surrounding vacuum in a specific way, causing the black hole to emit thermal radiation. This is called Hawking radiation. The temperature of this radiation is inversely proportional to the mass of the black hole. For a black hole the mass of the sun, the Hawking temperature is so close to absolute zero, it's essentially unmeasurable, far colder than the cosmic microwave background. For a black hole the mass of a mountain, it will be hot enough to glow in X-rays. For a black hole the mass of a bacterium, the temperature will be extreme enough to evaporate it almost instantly. The causal horizon at the leading edge of a superluminal warp bubble is not a black hole, but it is a causal horizon. And causal horizons, according to the mathematics of quantum field theory in curved space-time, also emit thermal radiation through a mechanism analogous to Hawking radiation. The difference is scale. A black hole's horizon is large. For a stellar mass black hole, it's measured in kilometers. The temperature is low because the curvature is gentle. The causal horizon on a warp bubble is tiny, potentially microscopic. The curvature is extreme. And the smaller the horizon, the hotter the radiation. Multiple physicists have analyzed this, including work building on calculations by William Unruh on radiation perceived by accelerating observers and subsequent analyses of superluminal warp geometries. The numbers that come out of these analyses are not comfortable. The radiation temperature inside a superluminal warp bubble, depending on the bubble's speed and geometry, could reach values measured not in Kelvin, not in thousands of Kelvin, but potentially in millions. At those temperatures, you're not talking about heat in any ordinary sense. You're talking about a gamma ray environment. The crew would be exposed to lethal radiation doses in fractions of a second. The ship's structure would be compromised shortly after. It's worth being precise here. These calculations involve assumptions about the quantum state of fields inside the bubble, and some details remain contested in the literature. But the general direction of the conclusion that quantum effects at the warp horizon create intense, potentially lethal radiation has been supported by multiple independent analyses. This isn't a fringe concern. It's one of the central unresolved problems in theoretical warp physics. The subliminal warp drive from the 2024 Fuchs paper does not have this problem. Without a causal horizon, there's no analogous radiation effect. The crew stays cool. This is one of the concrete, practical reasons that the slower-than-light solution actually matters. Problem 3. What the ship would do to its destination. The third problem was analyzed in a 2012 paper by researchers including Brendan McMonigal, Geraint Lewis, and Philip O'Byrne at the University of Sydney, published in Physical Review D. Their starting point: space is not empty. The interstellar medium, the space between stars, contains hydrogen atoms, dust particles, and various other forms of matter at very low densities. Not nothing, not even close to a laboratory vacuum, just extremely thin. As a warp bubble moves through this medium, particles interact with the leading edge of the bubble's geometry. In the reference frame of the bubble, these particles are being swept up in a subliminal bubble moving at modest speeds. These interactions are negligible, but in a superluminal bubble, something different happens. Particles that enter the compressed region at the front of the bubble get trapped there. The geometry of the bubble doesn't allow them to pass through to the interior, and as the bubble accelerates, they accumulate. High-energy particles already present in the interstellar medium, cosmic rays, get trapped and amplified. Over the course of a journey of even a few light years, this accumulation becomes substantial. When the bubble decelerates, when you arrive, all of that accumulated energy has to go somewhere. It goes forward, into whatever is in front of the ship when it stops. The McMonigal analysis found that the energy released in this deceleration event would be enormous, directed as a focus beam into the destination region, not scattered, directed And according to the paper, there is no upper limit on that energy. The longer the journey, the more particles accumulate and the more devastating their arrival. Even across short distances, the authors concluded the energy would be sufficient to destroy anything in front of the ship. The implication is uncomfortable. A superluminal warp ship arriving at a destination would, upon deceleration, effectively irradiate and potentially destroy whatever was there. Other spacecraft, habitats, planets. The paper's authors were careful not to sensationalize this. The scenario requires a superluminal bubble, which requires exotic matter, which we can't produce, so the practical threat is zero. But as a theoretical result, it's striking. The same technology that would let you cross interstellar distances in weeks would, upon arrival, deliver a concentrated beam of high-energy particles into the destination. You would be both explorer and destroyer simultaneously by the physics of the journey itself, the honest accounting. So here's where the faster-than-light dream actually stands. 3 independent physical problems: the control horizon, the radiation environment, and the particle accumulation, each of which, on its own, appears to make crude superluminal warp travel impractical or fatal. Together, they form a wall that is qualitatively different from the engineering challenges of building a rocket or a fusion drive. These aren't problems of insufficient technology. They're problems of physics. The universe appears to have arranged things such that the methods by which you might exceed the speed of light are also, by the same mechanisms, methods that would kill you or your destination. Whether this is a fundamental law or a feature of the specific geometries we've explored so far, whether some future configuration might avoid all 3 problems simultaneously, is genuinely unknown. There is no proof that is impossible. There's also no existing solution that avoids all of them. What we have instead is the subliminal result. The slower-than-light warp geometry that works within known physics, avoids exotic matter, and sidesteps all 3 of these catastrophes precisely because it never breaks the light barrier. It's slower, it's real, and in 2024, something happened that put even this theoretical, distant engineering challenge scale concept into a new context. Someone figured out what would sound like if one broke. The sound of a crash. In the summer of 2024, a team of physicists from Queen Mary University of London, the University of Potsdam, the Max Planck Institute for Gravitational Physics, and Cardiff University published a paper in the Open Journal of Astrophysics. The lead author was Dr. Katie Clough of Queen Mary University. The paper's title was What No One Has Seen Before: Gravitational Waveforms from Warp Drive Collapse. What they did was run a simulation. They took the Alcubierre Warp metric, the original 1994 formulation, and fed it into numerical relativity, software running on supercomputers. The same class of software used to model black hole mergers and neutron star collisions. They set up a stable warp bubble, then removed the conditions maintaining it, simulating what would happen if a warp drive suffered a catastrophic containment failure, a crash. In the mathematical sense, the bubble collapsed, and as it did, it disturbed the geometry of space-time around it. That disturbance propagated outward as gravitational waves, ripples in the fabric of space-time, identical in nature to the waves detected by LIGO from merging black holes, but different in their specific signature. The signal was a short, sharp burst, high frequency, distinct from anything produced by black hole mergers or neutron star collisions, which generate a characteristic chirp, a rising tone that sweeps upward in frequency as the objects spiral inward. The warp collapse produced something different, a brief, high-frequency spike, a crack rather than chirp. Dr. Clough, describing the work, was careful to note that she and her colleagues are skeptical about the likelihood of actually detecting such a signal. The study assumes a warp drive exists, which it doesn't. But the point isn't practicality, it's methodology, a new kind of search. Here is the interesting implication. LIGO, the Laser Interferometer Gravitational Wave Observatory, has been detecting gravitational waves since 2015. It has observed dozens of events: black holes merging, neutron stars colliding, compact objects spiraling together across billions of light years. Every one of these events produces a gravitational wave signal with a specific mathematical shape, a specific frequency range, a specific duration. LIGO is optimized for frequency range of those astrophysical events. roughly 10 to 1,000 hertz. Black holes and neutron stars, given their masses, produce signals in that window. The gravitational wave burst from a warp drive collapse would fall in a much higher frequency range, potentially hundreds of kilohertz or higher, depending on the bubble size and configuration. Current detectors are not designed to see that frequency range. They're the wrong instrument for the job. But the technology to build higher frequency gravitational wave detectors exists. It hasn't been funded at large scale. It hasn't been prioritized, partly because there hasn't been a compelling astrophysical reason to build one. Most natural processes that produce gravitational waves do so in the lower frequency range LIGO covers. What Clough's paper did was provide a new reason to consider it, not because we expect warp drives to exist, not because the researchers themselves think we'll detect anything, but because if any civilization anywhere in the observable universe has built a warp drive, and if that drive has ever failed, the collapse would have produced a gravitational wave signal that is, in principle, detectable, a signal that is distinctive, a signal that couldn't be produced by any known natural process. This is a new form of SETI, the search for extraterrestrial intelligence, not radio signals, not laser pulses, gravitational wave technosignatures, the acoustic fingerprint of alien engineering failures, propagating through the geometry of space-time, potentially crossing billions of light years to arrive at our detectors. Dr. Clough's own words on this were measured. She said she thinks it's sufficiently interesting to be worth looking, not that she expects to find anything. That is worth looking. In science, that's often how things start. Where this actually leaves us, let's be precise about what exists and what doesn't. What exists, a peer-reviewed mathematical solution, published in one of the leading journals in the field, describing a warp drive geometry that satisfies all the classical energy conditions of general relativity using only ordinary matter. It was produced by a legitimate research team, verified with numerical tools, and has been cited by subsequent work in the field. It is slower than light. What doesn't exist? Any physical warp drive, any material capable of withstanding the pressures involved. The solution requires a matter shell under stresses that no known material approaches. Any power source capable of supplying the energy required, which is measured in terawatts at minimum and likely far beyond that in practice. Any engineering path from current technology to a working prototype, even in theory. The honest estimate of the gap between the 2024 mathematical result and a functioning warp drive from the researchers who produced it is centuries at minimum, possibly millennia, possibly never, if some currently unknown constraint turns out to be prohibitive. What changed in 2024 is the category of the problem. Before Fuchs and his colleagues published their result, warp drives required something that doesn't exist: exotic matter with negative energy density. This placed them in the same category as perpetual motion machines, not just difficult, but forbidden, ruled out by physics, not merely by engineering. After the paper, a warp drive, a subliminal one, requires only things that exist in principle, even if we can't yet produce them at the required scale. It has moved from forbidden to extraordinarily difficult. That is not a small shift. The history of physics is, in part, a history of problems moving between those two categories. Heavier-than-air flight was once considered by serious people to be physically impossible. Nuclear energy was once considered an irrelevant theoretical curiosity. The detection of gravitational waves, proven by Einstein's equations to exist, but considered undetectable in practice for most of the 20th century, was finally confirmed in 2015, a century after the prediction. None of this is an argument that warp drives will be built. It's an argument that physically impossible and currently beyond our technology are very different statements, and that conflating them has historically not served us well. The question that remains open: there's one more thing worth sitting with. We are, as far as we know, the only civilization in this solar system. We may be the only technological civilization in a significant radius of space. Or we may not be. The Fermi paradox, the question of why, given the age and size of the universe, we don't see obvious evidence of other civilizations, has no agreed answer. But one of the variables in that question is travel time. If the speed of light is a hard constraint, then even a civilization 1,000 light years away would need thousands of years to reach us at any speed we know how to achieve. The galaxy is large. The distances are staggering. Absence of contact may say nothing about absence of civilizations. Warp drives, even subliminal ones operating at significant fractions of the speed of light, change that calculus. They don't eliminate the distance, but they make it traversable on timescales shorter than civilizational lifespans. A galaxy that takes millions of years to cross at chemical rocket speeds takes thousands at near-light warp speeds. Still vast, less infinite. And if some civilization, somewhere, solved it, fully solved it, superluminal or not, and if their ships have been traveling and occasionally failing for the past billion years, then somewhere in the data stream of the universe, in frequencies we haven't built the right instruments to hear, there may be a record of that, a burst of gravitational waves. High frequency, short duration, arriving from no known astrophysical source. We're not listening for it yet. We don't have the detectors. We don't have the funding. We don't even have a strong scientific consensus that we should be looking. But we have the equations. We know what the signal would look like. We know what instrument would catch it. Whether that's enough to make it worth building is a question about priorities, about resources, about what kind of knowledge we think is worth pursuing. It's also a question about what we're afraid to find, because there are two answers to the question of why we haven't heard a warp drive collapse anywhere in the observable universe. The first is that no one has ever built one. The second is that we've been listening on the wrong frequency. One of those answers is lonelier than the other. We don't know which one is true,